Dear students, today we are going to discuss mathematics paper 3rd year 5th semester linear programming problem. We will discuss first what is operation research and the scope of operation research and the importance of operation research as well as linear programming problem. Okay, and in this how we are going to form the linear programming problem whenever a physical problem is given. With the help of that we have to convert that physical problem into a mathematical problem. Okay, so that concepts we are going to discuss today now. Now see here, after learning these linear programming problem, coming to the main objectives of this chapter, the origination of LPP and the need and importance of LPP in mathematical modeling and the assumptions of linear programming problem and the formulation of linear programming problem. Let me discuss first introduction. The present day first life and the economic conditions of the world through a big challenge to the research and development community to provide the best solution to meet the demands of the society with minimal resources in our real life. Operation research, one of the most useful techniques, provides solutions to meet the needs of present scenario and demands of the current trends. It is quite interesting to know the origin of operation research. In fact, linear programming problem is one of the useful technique in operation research. Now coming to the importance of or the introduction part of linear programming problem. Linear programming problem is one of the mathematical modeling method used by army personnel during World War II and later it was improved for civilian purposes. To maximize the profits for the organization and to minimize the cost effectiveness, the method of linear programming problem is provided to be useful, and it is concerned with how to allocate or use the available resources, raw material, labor, machines, etc. in the best way in order to maximize the profit and minimize the cost limited constraints. The main linear programming problem is the mathematical technique for determining an optimal schedule or independent activities with the available resources. There will be a linear relationship between two or more variables where in the variables are directly proportional when a set of alternative is available, and if one of wants to select the best, then linear programming method is very helpful. And coming to the few applications of operation research. So actually this operation research is a wide subject. It is used in various departments, and here I am going to discuss few applications in accountancy, construction field, finance and facilities plannings and manufacturing, marketing areas, organization behavior, purchasing and research development area. These are the few applications of operation research. And coming to the basic definitions or the terminology in this linear programming problem. Coming to the first definition, linear programming problem. A mathematical technique for determining an optimum schedule of independent activities with available resources is known as linear programming problem. And in this, coming to the next, objective function. In a linear programming problem, the optimization, the meaning of this word optimization means whether the objective function which is to be either minimized or maximized is known as optimization. So, in a linear programming problem, the optimization linear function of variable is called objective function. So, what the function we are going to either minimize or maximize, that function is called optimization function. And coming to the constraints. So, based on certain constraints, we have to solve the given LPP problem. So, coming to the meaning of this constraint set is the rules used for operating the process are expressed as a set of linear equations or inequations. This set is known as constraint set. And decision variables. So, whatever the unknown variables we are going to take in that given LPP, that all unknown variables are known as decision variables, and always these decision variables are non-negatives. And coming to the characteristics of linear programming problem. The decision variables used in the problem must be non-negative, that is, it should be either positive or positive definite or 0, but it cannot be in terms of negative. And second one, the objective function of the linear programming problem should be described by a well defined linear function of decision variables. And third one, there must be a set of constraints which is expressed as linear equations or inequations. The linear programming problem should be provides a set of alternative courses of action. And some areas of applications of LPP. So, where we are going to use this linear programming problem in our general life. The diet problems, this is the one of the major important application. The diet problem and production mix problems and network problems and the airlines problems like cabs problems and oil and gas industries. In these areas, we are going to use regularly these linear programming applications. Okay. Next, coming to the how to formulate the linear programming problem means first they will give the one physical problem. By reading that entire physical problem, we have to convert that physical problem into mathematical problem. What about objective function? What about subject to the constraints? And what about non-negative conditions? We have to frame these 3 steps with the help of given physical problem. So, by reading that entire physical problem, we have to convert the problem into mathematical problem. That final mathematical problem is known as linear programming problem. That entire procedure is known as formation of linear programming problem. So, while going to prepare the or while going to convert the physical problem to linear programming problem, we have to follow certain rules and regulations or certain procedure. Now, coming to the step by step. First step, identification of unknown variables. This is the most important. So, by reading that entire problem, we have to identify what about decision variables or what about unknown variables. Based on that only, we have to define the objective function as well as constraints and whatever it may be. So, first step is identification of unknown variables to be determined to express them as a algebraic symbols. And step 2, identification of restrictions or constraints in the problem and representation of the same as linear equation or linear inequations, which include linear function of decision variables. And step 3, identification of the objective function or criteria function and its representation as a linear function of decision variables. This function has to be either minimized or maximized. Yes, it is one of the most important. So, objective function or optimization function means the given function we are going to either minimize it or maximize it. That is according to the given problem. It is a cost function or a profit function. Next, coming to the general form of linear programming problem. When we can say the linear programming problem is in general format. So, it consists again 3 steps. There will be objective function, constraints and non-negative condition. In objective function, the function it should be either minimized or maximized, and it is defined by maximum or minimum z equal to c1x1 plus c2x2 plus c3x3 plus data up to cn xn. If n unknown variables are there, here x1, x2, x3 up to xn are unknown variables are decision variables, and where c1, c2, c3 up to cn are the cost of these unknown variables. So, with the help of this I am preparing the objective function. So, either minimized or maximized z equal to c1 x1 plus C2x2 plus data up to Cn xn. This is objective function. And coming to the subject to the constraints. Subject to the constraints, if we have n unknown variables and m constraints. Yes, please listen this carefully. N unknown variables and m constraints, then the subject to the constraints will be in this format. That is a11 x1 plus a12 x2 plus a13 x3 plus data up to a1n xn less than or equal to or greater than or equal to or equal to. There here I put the symbol star. That star indicates either of these three formats. Either it may be greater than or equal to, or it may be less than or equal to, or it may be equal to. Any one of these three inequality or equality must be exist here in this star mark. That is star it is equal to b1. Similarly, second constraint a21 x1 a22 x2 plus a23 x3 plus data up to a2n xn either less than or equal to, again greater than or equal to b2. Like that we have to take up to m constraint. Last mth constraint will be a m1 x1 plus a m2 x2 plus a m3 x3 plus data up to a mn xn, again which is either less than or equal to or greater than or equal to or equal to bm. So here I am taking totally m constraints with n unknown variables. So this is the structure of subject to the constraint, and here all c1 c2 c3 up to cn are profit coefficient of xi's. That is x1 coefficient is c1, x2 coefficient is c2 up to xn coefficient is cn, and a is the coefficient matrix. The coefficient matrix of that a11 x1, x1 coefficient is a11, x2 coefficient is a21, like that a12. So we are preparing a1 aij is the coefficient matrix, it is constant. Similarly, bi, the right hand side matrix, it is the column matrix. Bi is the column matrix with b1 b2 b3 up to bm, it is also constant. This is the structure of general format of linear programming problem. That is, there should be objective function. As once again I am repeating, the general format of linear programming problem is there will be objective function. It is either minimized or maximized, and the form of this is maximum or minimum z equal to c1 x1 plus c2 x2 plus data up to cn xn, and subject to the constants are a11 x1 plus a12 x2 data up to either a1n xn either less than or equal to or greater than or equal to b1. Like that the mth constraint will be am1 x1 plus am2 x2 plus data up to amn xn. Why? Because I am taking xn, n unknown variables we have taken, and why I am taking amn, m constants we have. So the last inequation or equation will be am1 x1 plus am2 x2 plus data up to amn xn, either it may be less than or equal to or greater than or equal to bm. Right? This is the general format of LPP, and whatever the decision variables we are going to take, x1, x2, x3 up to xn, all these are strictly non-negatives. Okay? This is general format of LPP. Next, coming to the standard form of LPP. This is also one of the most important topic. While we are going to simplify the given LPP problem, we have to check out the given problem is in standard form or not. When we can say the LPP is in standard form. So first it should be linear programming problem, means it consists objective function, constraints function and a non-negative. So if this problem LPP, then we have to convert it into standard form. So when we are going to say an LPP is said to be in standard form, means the LPP must follow three steps again. So first one, objective function. In this standard form of LPP, the objective function is always maximum z. Yes, I will repeat once again. In standard form of LPP, the objective function is always maximization function. Okay. Suppose if it is minimum is there, let us suppose we have to convert this minimum function into maximum by multiplying -1. Okay. So if it is in the question minimum z is given, so we are converting this into maximization, means maximum z equal to minus of minimum z, so that it can be shifted to maximization function. So this is the first step. What about first step? The objective function is always maximum z. Okay. Next, second step. Whatever the constraints we are taking, just now we discussed that general form in LPP. There I have taken the constraints are either of the three formats, less than or equal to, or greater than or equal to, or equal to. But while going to convert into standard form, the constraints are always equality type only. If it is less than or greater than is there, by introducing slack or surplus variables. Additionally, we are going to introduce slack or surplus variables. With the help of that variables, we have to convert that inequations into equations. So, the constraints format is always equality type only. And third one, all decision variables or all unknown variables must be strictly greater than or equal to 0. If it is an unknown variables are there, x1, x2, x3 up to xn, x1 greater than or equal to 0, x2 greater than or equal to 0, and that up to xn is also greater than or equal to 0. If any LPP follows these three steps, then we can say that LPP, not only LPP, it will become in or it is in standard form. Okay. So, objective function maximum z, constraints are directly equality form, and non-negative conditions must be satisfied. So, this format is known as standard form of LPP. Okay. Next, coming to the two major definitions, slack variables and surplus variables. Okay. Slack variable means, suppose in a given constraint of the LPP, summation I equal to aij xij less than or equal to b. So, whenever the inequations are less than or equal to type, okay, whenever the constraints are less than or equal to type, we have to make them these inequality type into equations type by adding certain variable on left hand side of the inequation only. So, whatever the mathematical operation we are going to take, that should be operate on left hand side only. So, that we have to convert the inequation into equation. So, whatever the extra or additional variable we are going to add, that additional variable is known as slack variable. Okay. So, if aij xij less than or equal to bi, so this represents any inequation. We have to convert this inequation into equation by adding certain extra variable on left hand side only. So, it will become aij xij plus s1 is equal to b1. Here whatever the variable we are adding s1, that s1 is the slack variable. So, additionally we are going to add for converting inequation into equations. That additional variable is known as slack variable. Similarly, coming to the next definition, surplus variables. So, for surplus variables, the inequations must be greater than or equal to type. That is, aij xij greater than or equal to bi. Again, it is inequation is given. So, we have to convert these inequation into equation by subtracting certain variable from left hand side of the given constraint. So, that inequation can be shifted to equation. So, whatever the variable we are going to subtract, that variable is known as surplus variable. So, aij xij greater than or equal to bi. So, we are converting this inequation into equation. aij xij minus s1 is equal to b1. So, here s1 is we are subtracting, so that this inequation can be shifted to equation. So, this subtracting variable s1 is called surplus variable. So, these two are the two major definitions. While going to solve the LPP problem, these will play a major role. Okay? Please remember this. Next, coming to the formation of LPP examples. Okay? They will give the one physical problem. By reading entire that problem, we have to convert that problem, physical problem, into mathematical problem. So, read that entire problem. What about decision variables? From the decision variables, how we are going to prepare the objective function. After that, how we are going to prepare the constraints functions. Then, what about non-negative conditions? Let me discuss that formation of LPP with a few examples. Okay, I already explained the applications of LPP are play in diet problems, product mix problems, and oil and industry, and televisions, okay, electric field. All these are the few applications. So, I will going to take one example from that field only, diet problems. Okay, coming to the LPP problem, how we are going to form or prepare the LPP, formation of LPP with the help of this diet problem. As first, I will read the question. A person wants to decide the constituents of the diet which will fulfill daily requirements of proteins, carbohydrates, fats, and at a minimum cost. Yes, he is giving three quantities: proteins, carbohydrates, and fats at a minimum cost. Yes, in the question itself he is giving the minimum cost. With the help of this one, we have to prepare the objective function. Let me read the entire problem first. So, at a minimum cost, the choices is to be made from different types of foods. Again, he is giving the different kinds of foods. The yield per unit of these foods are given in the following table. So, see this table. In this, he is giving the 4 types of foods. Type 1, type 2 are 1, 2, 3, 4, 4 different types of foods, and yields per unit. On these 4 foods, he is giving the 3 formats, that is proteins, fats and carbohydrates, and whose cost per unit is giving the rupees in terms of rupees. So, first one, just here, first type food, proteins are 3 quantities or 3 units, and fats are 2 units, and carbohydrates are 6 units. For these 3, the cost per unit is 45 rupees. Similarly, second food, 4 proteins units and fats units are 2 and carbohydrates units are 4, and for these quantities is preparing the charge is cost per unit is 40 rupees. Similarly, third food and fourth food, and in the last row he is giving minimum requirements. As the meaning of this minimum requirements means, for proteins, by maintaining these 3 units, 4 units, 8 units, 6 units for each different type of food, he is maintaining the minimum requirement charge is 800. Similarly, fats 200 minimum requirements and carbohydrates 700. So, this is the table structure. Now, we have to formulate this as a LPP structure. Okay. Now, coming to this. First, here by reading this entire problem, we have to identify how many different decision variables are there. So, in this I am taking decision variables means I am going to take here 4 different foods are there. Food 1, food 2, food 3, food 4. So, for each and every individual food, I am giving the variable. X1 indicates first food, X2 indicates the food second, and food 3, I am giving the another variable X3. For food 4, I am giving the variable X4. Okay. So, let us suppose X1, X2, X3, X4 up to X3, X4 are the 4 different variables which indicates 4 different foods respectively. Okay. And these are the decision variables. Now, with the help of this, coming to the first objective function. How we are going to prepare the objective function? Yes, he is giving the cost per unit. See last column of the table. The cost per unit in rupees for 4 different foods. For first food it is 45 rupees. For second food it is 40 rupees. For third food 85 rupees. And for food 4 it is 65 rupees. And he is saying in the question itself, he is saying these costs should be minimized. So, we can choose the objective function is minimum function. So, the objective function is minimum of 45 into x1 variable, that is I am giving the first food is x1. So, 45 x1 plus 40 x2 plus 85 x3 plus 65 x4 is the objective function. See here. So, the objective function is minimum z. Therefore, minimum z is 45 x1 plus 40 x2 plus 85 x3 plus 65 x4. Now, coming to the preparing the constraints. Yes, see once again see this entire table. So, with the help of this table only we have to prepare the constraints. So, how to prepare the constraints? Yes, he is giving the 3 different requirements of the proteins as well as fats as well as carbohydrates. With the help of only proteins we have to prepare the one inequation. With the help of only fats we have to prepare the one more equation. Inequation. Similarly, with the help of only carbohydrates we have to prepare the one more inequation. So, coming to the first constraint based on proteins. Yes, based on proteins per daily I am preparing the one constraint is 3x1 plus 4x2 plus 8x3 plus 6x3, and he is saying 800 minimum requirements. As here 800 minimum requirements means it should be either 800 or more than 800. Minimum is 800 is giving. So, the value will be begin from 800 to onwards. So, that is why I am taking here inequation is 3x1 plus 4x2 plus 8x3 plus 6x4 must be greater than or equal to 800. So, this is also important. Why I am taking greater than or equal to? Why can't it is less than or equal to, or why can't it is equal to? Why? Because see again table. In this clearly is giving the minimum requirements must be 800 means either it should be 800 or above 800. That is why I am preparing the equation 3x1 plus 4x2 plus 8x3 plus 6x4 must be greater than or equal to 800. This is the first constraint based on proteins. Okay. Similarly, second constraint we have to prepare based on fats. Second constraint 2x1 plus 2x2 plus 7x3 plus 5x4. It is also minimum requirements, means greater than or equal to 200. Yes, once again I will repeat. The second constraint based on fats is 2x1 plus 2x2 plus 7x3 plus 5x4 must be greater than or equal to 200. This is second constraint. Similarly, we have one more food item, that is carbohydrates. Based on carbohydrates only, also we have to prepare one more constraint, that is for food 1 it is 6, for food 2 it is 4, for food 3 it is 7 units, and for food 4 it is 4 units. So, the constraint will become based on carbohydrates 6x1 plus 4x2 plus 7x3 plus 4x4 must be greater than or equal to 700. These are the three constraints based on proteins, based on fats, based on carbohydrates. So, these are the subject to the constraints. And what about last step in LPP? Non-negative condition. Okay, here how many variables we have? x1, x2, x3, x4, that is 4 different types of foods is there. So, whatever the variables we are going to take, that must be always greater than or equal to, because food, it is a food items. It can be in terms of less than 0, that is it cannot be in terms of negative. Therefore, it is x1 greater than or equal to 0, x2 greater than or equal to 0, x3 greater than or equal to 0, and x4 is also greater than or equal to 0. This is non-negative condition. So, this is the formation of LPP. So, here the final structure will be, so objective function is minimum z equal to 45x1 plus 40x2 plus 85x2 x3 plus 65x4, and constraints, subject to the constraints are based on proteins. What is first equation? 3x1 plus 4x2 plus 8x3 plus 6x4 must be greater than or equal to 800. Based on fats, second constraint 2x1 plus 2x2 plus 7x3 plus 5x4 greater than or equal to 200. And last constraint based on carbohydrates, 6x1 plus 4x2 plus 7x3, 4x4 must be greater than or equal to 700. And a non-negative condition, last condition, whatever the unknown variables we are going to take, that must be strictly non-negative. That is x1, x2, x3 and x4 must be strictly greater than or equal to 0. So, this is the formation of LPP for given table or given problem. Let me discuss one more example. Yes, a television problem. Of course, it is a television manufacturer is concerned. I will read the first questions here. A television manufacturer is concerned about how many units of 3 types of portable television sets should be produced during the next time period to maximum profit. As in the question is giving maximum profit. Maximum profit means objective function should be maximum z. So, in this also is giving 3 types, 1, 2, 3, 3 types, and assume 3 variables, x1 with the first type, x2 is the second type, x3 is the third type, and whose available time is 2000, 1000, and it is raw material is available 2000. Time is constant based on 1000, and individually he is giving minimum requirement 200, 250, 100, and last profit amount is 10, 14, 12. So, the inequations will be like this, or the LPP will be like this. So, objective function is, in the question itself is giving maximum profit. So, maximum z equal to objective function, maximum z equal to 10x1 plus 14x2 plus 12x3, and subject to the constraints are, here we are going to prepare the constraints based on raw material, based on time, and individually minimum requirements. First constraint based on raw material 1.0 into x1, 1.5 into x2 and 4.0 into x3, it must be less than or equal to 2000, because he is giving the available time. Okay, this is the first constraint based on raw material. Similarly, the second constraint based on time interval, that is 2x1, 1.2, 2x1 plus 1.2 into x2 plus x3, 1 into x3, and it must be less than or equal to 1000. And last 3 constraints will be individually, you will get the minimum required time is given. So, x1 200 into x1 must be greater than or equal to 0, and 250 x2 greater than must be greater than or equal to 0, and 100 into x3 greater than or equal to 0. These are the 3 constraints here. First constraint based on raw material 1x1 plus 1.5 into x2 plus 4 into x3 less than or equal to 2000. Second constraint 2 into x1 plus 1.2 into x2 plus 1.0 into x3 must be less than or equal to 1000. And last three constraints are based on S. What about based on minimum required? So x1 greater than or equal to 100, x2 greater than or equal to 50, and x5, x3 greater than or equal to 100. And last non-negative condition, all decision variables type 1, type 2, type 3, that is x1, x2, x3 are strictly greater than or equal to 0. Okay. After listening this, you able to frame how we are going to convert the physical problem into linear programming problem, that is LPP structure. Okay. Thank you.